Now, in this tutorial, we're going to be looking at velocity time graphs. Now, I've included a few other types of graphs here as well because they're all important. Okay, so to start off with, we've got position time graph, our velocity time graph, and our acceleration time graph. Okay, in all three of these cases, we care about the gradient of our line, okay, and also the area under the graph. Okay, so for a position time graph, our gradient is equal to our velocity. Okay, and the area under the graph has actually no relevance in this case. For a velocity time graph, our gradient gives us our acceleration, and that's actually our instantaneous acceleration. Okay, and the area under the graph is our displacement. Okay, for our acceleration time graph, our gradient has no relevance, but the area under the graph is our velocity. Now, the area under the graph must be taken to be positive, and we need to be careful when the graph goes below the x-axis. So by that I mean, if we have something like this, and we need our time up here, so this might be our velocity and time. Okay, so this would indicate that we're slowing down, we get to a point and then we turn around and go back. Okay, so when we're trying to find our displacement, well, if we work out the area under here, that would be positive, but if we work out the area under this part would be negative. So we need to make that positive and add it together for our displacement. Okay, just a few formulas to remember. So the area of our triangle is a half times our base times our height. Okay, the area of a rectangle is length by width, and the area of a trapezium is a half a plus b on h. Remember, for our trapezium, okay, we're saying that that's a, that's b. Okay, and we're times it by our height here. Okay, and by a half. Okay, so we'll move on to our work examples. Okay, so I've got a little jump start by studying our velocity time graphs. So we have a train uniformly accelerates from a velocity of 25 metres per second to a velocity of 50 metres per second in a time of 20 seconds. This is where I've got my velocity starting at 25, going to 50 over a time of 20 seconds. We want to find the acceleration of the train and the distance travelled by the train. Okay, so acceleration is our gradient of this line. Okay, so remember, m equals rise over run, which is y2 minus y1 over x2 minus x1. Okay, so our gradient, okay, which actually we'll just call our acceleration because we know that's what it is. Okay, y2 is going to be our 50 minus our y1, which is 25, over x2, which is 20 minus 0. Okay, which means we have 25 over 20, which is 1.25 metres per second squared for our units or acceleration. Okay, and we want the distance travelled. Okay, so we're going to use one of our constant acceleration formulas. So we're going to use s equals a half of u plus v t. Okay, so s equals a half. Initial velocity was 25. Final velocity 50 over a time of 20. Okay, and when we work that out, we get 750 metres. Okay, so we'll flip over to our last worked example for this section. And again, I've done up the velocity time graph, but I'll read through the question first. So have Puffin Billy runs on a straight track between Belgrave and Lakeside stations, which are 10 kilometres apart. It accelerates at 0.1 metres per second squared from rest at Belgrave until it reaches a maximum speed of 8 metres per second. Okay, so here we've got our gradient of 0.1 till we get to 8. Okay, for some time it's going to stay at 8 metres per second, okay, and then it's going to decelerate, okay, at 0.15 metres per second. Okay, so we're slowing down, okay, until it comes to a rest. And we want to find the time taken for the Puffin Billy journey. Okay, so we've got our velocity time graph here. So what we're going to do is work out our displacement. Okay, basically we're saying, well, we're going the area under this triangle for a start. Okay, so we'd be a half times our base, well that's going to be T1, times our height, which is 8, Okay, then we're going to add on this area here, okay, which would be our half times our, sorry, it won't be half, so we don't need our half. Of course, because it's just a rectangle, so it'll be T2 take T1 times 8 plus 8, and we need this area here. Okay, so that'll be our half times 8 times, and we need to call this T3. T3 take T2. Okay, so we had half T1 times 8 for this one. We had T2 take T1 times 8 for this one. And we had our half times 8 times T3 take T2 for that one. We know that that's equal to 10,000 metres or 10 kilometres. Hey, so we need to determine T1, which we can do, okay, because we know that the time taken for it to accelerate here, we can work it out because our gradient is our rise over run. So we know that 0.1 equals 8 over our T1. Okay, therefore our T1 has to equal 8 over 0.1, or that T1 equals 80 seconds. Okay, and we can do the same idea here. Okay. So we want the time to decelerate. Okay, so we can say then that we're going to be for that one, sorry, with our A equals 0.15, okay, we know 0.15 equals 8 over T again. Okay, and we're going to when we do that, we get this time to be 53 1/3 seconds. So it's going to be 53 1/3 seconds to slow down there. Okay, so we can start to work things out a little bit here. Okay, so what we're going to say is we're going to move up here. Let T equal T2 take T1. Okay, so that means in our equation here, we get a half times 8 times 80 plus T times 8 plus a half times 8 times 53 1/3 equally 10,000. So we worked out this time here, that was our 53 1/3, so we've put that in, and we've worked out this time here, and we've put that in as our 80. Okay, and when we work that out, run through and solve for T, then we get T equals 1,183.33. Okay, and so we know that that's our time in here. So for our total time then, total time is going to be 1183.33 plus our 80 plus our 53.33 or 53 1/3. Okay, and we get 1,316.66 seconds. Okay, for the Puffin Billy ride, or you can convert that to minutes and seconds. It's 21 minutes and 57 seconds. Okay, so that's all we have for this section. Okay, so hopefully you get to the questions.